Thank you all for coming. It's interesting, actually, segue from the previous talk. We'll see a little bit why. Why my talk was originally titled "The 5 Things That Bit Me in the Ass" while doing anomaly detection, but the organizers asked me to change that. So now it's 5 things that I learned while building anomaly detection tools. A quick preamble. I'm not a data scientist. You know, I do play one sometimes, you know, at these talks, but I'm not really. I'm just an engineer who wanted to get some stuff done and kind of stumbled into this to a certain extent. I learned many, many more things than the 5 I will talk about today, but unfortunately, a lot of those things I can't talk about because lawyers. But, you know, if you're around later and I happen to be drinking, you know, we can talk about some of those things. If you've seen any other of my talks, I usually beat up a lot on parametric and Gaussian type of techniques and so on. I also give you a lot of techniques that actually work. The organizer asked me to do a little bit different this time. They wanted me to give sort of like lessons learned type of message. So I'll be concentrating. There won't be too many like very useful techniques for you to take home. It'll be more, all right, you know, beware of this, beware of this. I learned this, and I learned that kind of stuff. Finally, all the data that you will see there is actual real data. It's data from my users or from my own networks. There are no labels on the y-axis because to me it almost doesn't matter. It could be unicorns or it could be, you know, packets per second. It doesn't really matter. What's fundamental, what's really important is the technique itself. I also have to remember to slow down. So if I start getting, I'm used to this. If I start getting way too fast, talking too fast, you know, some of you guys need to go. This is the sign usually that my team tells me when I'm at the office. And I always put a cat there because apparently everybody loves cats, according to my daughter, and that's a surefire way to get a good presentation. So with that out of the way, just quick intro to myself. Thank you for the introduction. I'm a founder and CTO of a company called Metafor Software. Pardon the layer look here, but it's just really cold in here, so I had to put something under my T-shirt. I was a founder and CTO of a company called Layer7 Technology before Metafor, doing mainly API and security management. I was acquired by CA last year. Thank you, CA. I managed to escape to start another company. Before that, I was at Saffron Technology, did a lot of hardcore pattern recognition. As you mentioned, I was IBM chief architect for service-oriented architecture team. Spent a lot of time in SOA, writing security standards and so on. I've been building large-scale systems for a very long time. I know everybody tells me I look a lot. I'm older than I look. But anyway, so just as an aside, if people like patterns, Metafor was named Gartner Cool Vendor and all my other companies too. So that's an interesting pattern for people who are interested in patterns. I'm actually kind of proud of it. Anyway, so why did I want to do anomaly detection? A variety of reasons, but you know, a lot of people, you know, end up watching screens on what I call the wall of charts. Everybody has a wall of charts that they sit and watch. You know, we talked about it in the previous session, this visualization. This cannot scale. We all know that can't scale. You know, you can watch 1, 2 charts 24/7. You have a team watching them, but after a while, you know, things are going to fall. Leads to what we call alert fatigue because you just, you know, you're getting pinged. You know, how many of you get, like, have pingdom or any of those things, and you get paged when stuff goes down? Thank you. How many of you go, like, say, 2 days without an alert? Wow, that's very good, actually. I don't. So maybe I need to twiddle my filters a little bit better. But in essence, you know, we need to automate the detection of all those anomalies in our systems. And that's why we look at what's called anomaly detection. It's the search for items or events which do not conform to an expected pattern. And that's really, really important. Really, in bluntly, what you want to do is you want to know automatically when some of your metrics that you're collecting goes wonky, really. That's what it really comes down to. So without too much preamble anymore, let's just get to those things one thing at a time. Okay. The first thing is that I learned is that your data is not Gaussian. Just a quick sort of basic thing about, you know, what a Gaussian or normal distribution looks like. It's really the distribution of your data looks like a bell-shaped curve. We've all heard of the bell curve. So it has a median, which is somewhere here. That's not working. But anyway, it has a median. You know, it has a mean and a standard deviation. right? So you can, and the mean could vary, and the standard deviation, which is the spread. So here I have a couple different distributions that have various means and various standard deviation. It's the spread away from the mean. That's what a normal or Gaussian distribution looks like. As an example, this is a metric from one of my users. You can't see the x-axis, which is irrelevant. And this is actually normally distributed data. Now, I just want to make sure that the data itself does not look like a bell curve. Its distribution looks like a bell curve, right? This is what the actual data looks like. There's tons of ways, if you use R or Octave or MATLAB or whatever, there's tons of ways to figure out if your data is Gaussian. But one quick and dirty way is to do a quick histogram. And the histogram should look something like that. There's a mean. There's a bit of a tight spread. It's unfortunate that the bottom is not really shown on the screen. But regardless. So you get a feel that this kind of data is Gaussian. This is very, very, very rare. The reason there's a normal distribution or Gaussian distribution are very, very powerful, very useful, because I can make very powerful predictions because of these statistical properties of the data. If my data is Gaussian, I can make very, very good, very powerful, very precise type of predictions. I can also easily compare different metrics that come from different sources because they have similar statistical properties. And there's a huge body of statistical work that is on parametric techniques for normal distributed data. So there's very, very good if your data is Gaussian. A lot of data from naturally occurring processes exhibits those kind of properties. The distribution is bell curved. You've got population height, population IQ distribution are Gaussian, of course, except for us. We're all above average. Everybody here is above average. But widget sizes, weights, whatever in manufacturing, all manufacturing processes produce data that is Gaussian. What's not is your metrics. And why is that important? That's really important because, all, if not most, of the analytics tools that you will be using make two fundamental assumptions. We'll look at the first one now. The first fundamental assumption that most tools make is that, your data is normally distributed. It has a useful and a usable mean, and it has a useful standard deviation. So these are what's called parametric techniques. And almost everything you're going to look at has some make parametric assumptions to it. So then they use a lot of tools that are parametric that actually make these kind of assumptions. So one of these techniques is the 3 sigma rule. I've probably heard of the 3 sigma rules. The 3 sigma rules is based on the assumption that your data is Gaussian, which means that 68% of the values lie within 1 standard deviation of the mean, 95% of the values lie within 2 standard deviation of the mean, and 99.73 of the values lie within 3 standard deviation. So anything else outside of those 3 sigmas, 3 standard deviation away from the mean, is considered to be an outlier, right? So if you know that, if the data is Gaussian, and you know that, it has a pretty stable mean, it has a standard deviation, so you can safely make the assumption that anything 3 sigma outside of real is an outlier, right? And that's why, you in all kinds of manufacturing, whatever, you can safely make these kind of assumptions, draw these lines, and then reject any widget that is outside of that particular height. Very, very simple. It works really, really well, except in your metrics, right? Because your metrics look like this. This is an example of, again, real data. I'm sure all of you have seen this kind of data, again, in your systems. This is what the distribution looked like for that particular data. It's not even close to being Gaussian. The mean is meaningless, and the standard deviation is totally meaningless, right? So when I want to use a 3 sigma type rule on this data, the red up there is the alerts that I get. I'm getting alerts all the time, right? So then, not in this talk, but in another talk, I've given another talk before where I go into a lot of detail about other techniques that you can use, like exponential smoothing, double exponential smoothing, Holt-Winters, which are a lot more sophisticated than 3 sigma. So I ran Holt-Winters on this kind of data, and Holt-Winters also doesn't work because you're still getting alerts all the time, right? So it's because of the assumption that all these techniques make about the data, which actually happen not to be true in real life. So that's one really, really important lesson. That's probably the first lesson that anybody should think about when they're looking at these kind of techniques. Or worse, something like this happens in your data, where it's running along, and then something happens, and your volume, whatever metric, drops down. Now, 3 sigma, and this is what the frequency for that looks like. Again, not even close to being Gaussian. And if you're using 3 sigma type of alerts, then you're going to draw the line somewhere, and you will get alerted at the right places while your metrics are kind of behaving. But then when you get that drop over there, nobody's visiting your website anymore for some reason. There's a competitor that's better. You're not going to get alerted unless you're sitting there and watching. And if you got 10,000 of these graphs all over the place, you're going to miss that, right? So that's really, really bad. That's one of the things that will happen. Again, you can run any kind of Holt Winters, exponential smoothing, whatever you want on that kind of data. You're not going to get any better. So that was thing 1. Thing 2 is that yesterday's anomaly is today's normal. Again, why is that important? Because, which leads us to the second assumption that most analytics tools make about your data, is that supervised learning techniques. The data is what's called probabilistically stationary. And that's why, so you've got parametric techniques that make the assumption that data is Gaussian. You've got supervised learning techniques that make the assumption that your data is probabilistically stationary. Now, that's a big word. I stumble on it. So what does it actually mean? Remember the data that I showed you early on, one of those metrics that actually happens to be Gaussian and has a bell curve normal distribution? The interesting thing about it, the beautiful thing about this kind of data is that no matter where you look at it, you take the first week, you take a month ago, whatever it is, the characteristics are still the same. So it's stationary from a probabilistic perspective. That's what stationary means, right? So then anywhere you look at the data, you look a week ago, a month ago, whatever, the data, underlying characteristics of the data don't change much. It still has the same mean. Again, you can't see the bottom, but I can. It still has the same mean, the same kind of tightness around the mean, the same standard deviation, and so on. So which is beautiful because, again, you can actually make all kinds of predictions and really powerful analyses on that data. So stationarity, however, is not a realistic assumption in large complex systems that we're dealing with. You will rarely find, unless your system is very, very stable and nothing is going to change in that system, most of the time, your data is not going to be stationary. There's this thing we call concept drift. It's very, very common. You can look it up on Wikipedia. It's an interesting, definition, which is the statistical properties of the target variable, which the model is trying to predict. My emphasis here, change over time in unforeseen ways. This causes problems because the predictions become less accurate as time passes. Anytime there's a change in fundamentals, these kind of techniques just don't work. And that's called concept drift or mean shift or what have you. So that's a really, really important lesson to learn. So a lot of non-parametric techniques used in machine learning use what's called supervised learning. And that's a general set of techniques that try to infer a model based on some labeled set of observations. So you have a training set where the data is labeled. You say, all right, this is normal, this is not normal, or this is normal, this is fraudulent, right? So you actually labeled the data, or you can make labels like this is red, this is green, whatever it is, you actually assign labels, and you feed that data into the system. And the system, as the data comes in, starts learning from that data and implicitly infers an internal model, an internal representation of that data looks like. Once that system is trained, it has enough of a complete model. There's all kinds of issues with overfitting and underfitting. Well, I'm going to ignore in this particular talk. Once you have that model is inferred, then you can let it loose in the wild on production data that's coming in. And because it has made that inference about what the model looks like, as real data, unlabeled data comes in, it can actually make, start making label and detecting anomalies based on the known set of anomalies that it has learned over time. Okay? Which is great if your system is stationary, but then you get stuff like this. Again, this is real data from one of my users. They made a change in one of their features, and everybody loved it apparently, and then wham, this became their new normal. This was the old normal, and it was running along quite nicely until this became their new normal. And when you have the new normal, any kind of supervised learning technique is going to fail. They're going to get alerted all the time. Does not recognize the new normal as normal. Right? I think in this case I use support vector machines or some kind of neural network. I can't remember exactly, but regardless, it's supervised learning. You give it a training set, it learns that training set, and then it applies the model that inferred on the data, and then something changes in your fundamentals, and then it goes haywire. It cannot recognize anything more. You have to throw it out. Right? So that's why it's really, really important to be aware of these kind of things. Just as it happened. And that's, as an aside, that's the beauty about not writing your presentation way in advance. I just finished writing it about a couple hours ago, in that you can incorporate new stuff, breaking news, into your presentation. So very, very recently, just a few days ago, Twitter actually wrote a really nice blog about a piece of code that they put out. I don't know if anybody uses R here or something similar. Yeah, it's written in R, and they talk about what's called breakout detection, right? Which is the same concept, breakout detection, or what's called mean shift. And in essence, it allows you to detect that kind of stuff, because it happens all the time at Twitter and elsewhere. And pretty much a lot of your data is going to have some kind of concept mean shift or some kind of concept drift, right? So you can go check out the blog. It's really very nicely written, and check out the code if you want. So that's that about thing number 2. So am I going fast, or is this a good pace? OK, good. All right. If you want to ask questions, you can, but as we go through the things one at a time, or if you want to save them till the end, we can do that too. Thing number 3, saying Kolmogorov-Smirnov is a great way to impress your friends. That's one thing I learned everywhere I go. I can say that, and people go, oh, wow, So why is that important? Because it's really important to impress everybody. So, but all kidding aside, you need to have non-parametric techniques. And non-parametric techniques, in that they make no assumption at all, but the underlying characteristic of your data, are really, really essential for you in your effort to understand what's going on in your data. You cannot use techniques that are parametric that make assumptions about Gaussian or any kind of other distribution. You have to use non-parametric technique. And KS is probably one of the best techniques that you can use on your data. So I'm going to make an exception and actually go into the details of a particular technique for this talk. I hope I don't get kicked out. So Kolmogorov-Smirnov also, if you even want to be cooler, you can just say KS. Is a non-parametric test in that it makes absolutely no assumption about the underlying distribution of your data. And the main purpose of KS is to compare two probability distributions. Now, the important thing about KS is that it doesn't measure the distribution, actually the density function. It actually measures the cumulative distribution. In essence, it's the integral under that curve of probability distribution, right? So it starts as 0 and it tends towards 1 as it goes to infinity and you collect all your data, right? So what it does is measures the maximum distance between two cumulative distributions of two different data sets. And that distance gives you an indication of how similar or dissimilar those two data sets are, in essence. And it can be used to compare periodic or seasonal metric periods, day to day, week to week, month to month, if you have seasonality. And by performing that comparison, you can actually detect anomalies if some of those data that should be behaving similarly is different. So let's take a look at that, at KS, how it works on that particular data set that I showed you before, right? So that data set looks like this. And if you were able to see the, maybe if I raise my laptop a little bit, you can, but no, I guess it doesn't work. So you'll notice, and my pointer's not working either. Oh, it's working now. Okay, so you'll notice, for example, actually what this is really is, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday, right? So it's real data from actual real stuff. And then something happens around here. So one way to use KS is to create these windows. So let's pick windows being, every Tuesday, and move those windows along. And those windows from week to week to week, should the data, the probability distribution of that data, the density function sort of that data, should be kind of similar. This is where KS really, really shines. So let's pick 3 different windows and see how you would apply KS to that kind of distribution, right? So the data from the 2 similar windows, this window and this window, looks like this when you superimpose them. General characteristics are kind of similar. Now, if we look at their cumulative distribution functions, it looks something like that. And the maximum distance is somewhere around here. So that tells us that the data is kind of similar in its characteristics. Look at the data from the windows that are very, very different. Even though it's the same, it's Tuesday. Both are Tuesdays, let's just say, right? And you look at the cumulative distribution function, the distance is huge between them. Now, if we go back and look at these windows and move them in time, make them as sliding windows, constantly computing what the distance is, what the KS distance is between those windows, what you will get is a graph that looks like this, right? And all of a sudden, when you hit that Tuesday where the data is very different, is going to go off the charts. And this is a strong indication of an anomaly, right? So if I were to take that and apply it to that data set, you get a couple of anomalies here that it hits, and then bang, it goes off the charts when your data, again, like I said, people don't go to your website anymore, as it happens, right? So you get it. So that's a really, really interesting technique, and I kind of slid it in there even as a lesson learned because I really like talking about it. It's really important. But that's just an example of the things that you can do that is non-parametric, unsupervised, and that works really, really well. Thing number 4, I'm trying to go, scope and context are really, really, really important. Take scope and context into account. Okay, so I have another set of data here. Is this normal? Yeah, I don't know. Look at it at a wider scope, right? And again, is this normal? I don't know either. If I ran some kind of anomaly detection system, take your pick here. A lot of techniques would work almost equally well here. RF, KS, whatever. All that stuff they would trigger on this for sure, right? Now, look at a wider scope. Right? Now, all of a sudden, maybe this is not an anomaly anymore. This is something that occurs on a regular basis. Right? So context is really, really important. Now, the question is, do you want it to trigger every weekend? As it happens here, this is actually happens to be the weekend. Do you want it to trigger as an anomaly every weekend? Or do you want it to learn from the first time it sees this, and then would this become more accurate? Again, it's a little bit up to you, but it's really, really important to take these things into account because this kind of context is really, really important. And you, more than anybody else, knows what your data looks like. So the lesson from here is that use domain knowledge. Use knowledge about your domain. There's nothing wrong with inserting domain knowledge into those algorithms. There's absolutely no algorithm that will work on everything. Not at all. If anybody says so, let me know. Actually, it'd be interesting. But know your data and know its general patterns. So, for example, is there periodicity or seasonality in your data? And if you think that there is, use that to your advantage. Come up with some algorithms that actually are really, really good on seasonality and periodicity. If there are some known events, for example, you've got some maintenance or backups coming along, right? If you have those kind of events, incorporate them. So apply the appropriate algorithms, taking into account enough scope for periodicity to appear, and then customize your alerts to take into account known events. If you know there's going to be a maintenance coming down, you don't really need to wake up everybody at 2 a.m. because one anomaly detection system started going haywire, right? So these kind of things are really important. So context and scope are really, really important. and domain knowledge incorporated into everything that you do. The last thing I want to talk about is this concept of no data does not mean no information. Right? So some data channels are inherently non-chatty. We don't always have the luxury of always generating non-zero values. Sometimes communication between two endpoints is quiet. That's not a bad thing. There's a lot of useful information to be gathered from the fact that nothing is happening on a particular channel. And which is great to know, but the problem is that a lot of time series analytical techniques utterly fail miserably when there's no values, there's no data, or not enough data. Like a lot of data is the same. So whether it's looking at random forest, adjusted box plots, or a whole bunch of other techniques that you use in anomaly detection on time series, they fail completely when they don't have a lot of data to work with. For example, any kind of field partitioning technique will fail. There's no question about that. So this is, again, an example of data, or one of the hundreds and not thousands of metrics that we collect on chatter between endpoints, for example, right? Oops, sorry. So all this data here is either zero, no data being collected, or zero, or the same, right? And RF will definitely fail. A whole bunch of techniques will fail on the data, or if there's not enough value, because there's not enough value to partition the field, to start building classification of the data. So RF will fail. Other techniques like box plot or adjusted box plots will not fail, but they will give you the results that are useless. In essence, what they're saying is all the data is here. And when you're looking at the quartile, because box plots does not use mean, they use median, which is a lot better measure when you're looking at these kind of things. And in essence, what it's saying is that every point that is non-zero is an anomaly, which is not right. Okay? So what do you do in this case? This is what the frequency histogram of that kind of data would look like, right? It's very, very heavily geared towards the low volume or the zero volume data, and then the long tail at the other side is the quote-unquote anomalies, right? So what you can do are very, very simple things like a lookup table, looking at the priors of that channel, and building a lookup table of values, and then partitioning based on lookup tables. Very, very simple technique. Doesn't use any kind of complicated math or or field partitioning and all that kind of stuff. And in that case, it actually gives you really, really good results, right? So the lesson here is don't be an analytics snob. Not everything needs to be Kolmogorov-Smirnov or triple exponential smoothing or Holt Winters or any of that kind of stuff. In a lot of cases, these techniques just don't work on sparse data sets. But sparse data is very hard to analyze using your typical analytical techniques, but it conveys some very, very important information. And sometimes just the simplest rules and thresholds and lookup tables will work really, really well. So again, don't think you have to use anything really complicated to get results done. That's pretty much what I wanted to talk about today. Just sort of to recap, your data is definitely not Gaussian. I mean, I bet you anything. Well, I shouldn't say that. I'm a betting man, but I'll bet you anything that a lot of your data is not Gaussian. How's that? To be safe. It's just not. Look at it. Take a look at it. Use some simple tools like histograms or whatever. Take a look at data. Understand the characteristics of data, and make sure you're not using techniques that make that kind of assumption. Yesterday's anomaly is today's normal. Concept drift or mean shift or breakouts will happen in your data all the time. There's really, really good techniques that you can use to detect for that. KS is really, really cool, really powerful, really useful. If there's one technique that you can take out of this, you can go and apply it on your data, especially if there's periodicity in your data, it's KS. Scope and context are really, really important. Use domain knowledge. There's nothing wrong with that. If your data has periodicity in it, use techniques that are periodic, that leverage that periodicity. If you know there's upcoming events, use those events to squelch some kind of your alerts and things like that. So incorporate previous knowledge, incorporate domain knowledge into your alerting and into your anomaly detection techniques. And then finally, no data does not mean no information. There's a lot of value in sparse data sets. And unfortunately, a lot of the analytics techniques that people use just don't work or fail miserably when given sparse data sets. But it doesn't mean you should be an analytics snob. Just use some kind of simple rules, look up tables, whatever you want. There's tons of really, really simple, low-hanging fruit type techniques that work on sparse data sets. But having said that, analyzing sparse data sets is still a really, really hard problem. But anyway, so that's kind of my quick talk for today. Quick shout out. I know they're not here, but I like to mention them to my guys back in Vancouver, Fred Zhang and Iman Makaremi, who helped me out a lot in producing the plots and so on. And that's it for me. Questions? Questions, questions, questions? I'm not going to give you a long window for questions. If no question, we'll leave.
So which of those techniques do you recommend combining with, say, A/B testing, which we find particularly useful with deployments?
Well, A/B testing is a perfect use case for KS, okay. Right?
Yeah,
you've got two data sets that you want to compare how similar they are. KS is a great test of similarity, right? Just, again, it's as if you planted that question from before. Yeah, for sure.
Hi, Toufic. Mark Curini. Good
Hi.
to see you.
Hey, Mark. Yeah.
So that's a great talk. I think we definitely need more of this knowledge disseminated amongst the sysadmin community, especially people doing monitoring all the time.
For sure.
One thing that I think is important, obviously, and you go to great pains to sort of mention that obviously there's no one size fits all, and you're talking about ensembles of techniques.
Yes.
Right. The one thing with KS is, and we know this, right, is that, and a lot of non-parametric techniques, is that it does make some assumptions about the data, or at least it makes assumptions about how you're sampling the data.
Yes.
Right. So they need to be identically distributed and independent. You can work.
There's bootstrapping.
These. You have to be careful. Is all I'm really saying. That's
totally
just
agree.
The one thing that
Yeah.
because, but anyway, we'll talk more offline.
Yeah, definitely. So just to sort of expand a little bit on what Mark said, there's always assumptions that you're going to make, even if they're subtle or implicit assumptions. There are techniques around them, like there's bootstrapping techniques around KS and things like that, but. And you're right. If that was not explicitly stated, let me state it explicitly here. Although I did say there is not one algorithm that's going to work for everything, right? Look at a variety of different algorithms. Make sure you're not using parametric techniques when your data does not have, does not lend itself to parametric techniques. Things like that are really important. But you're right. I'd love to continue that conversation. And thank you for the endorsement. I do think that we need to have a lot more of that kind of knowledge start seeping into the community, because what ends up happening is that we end up using tools, whatever, without understanding how they work, and then we complain that they don't work well, right?
Can you recommend any specific tools or software to do this kind of alerting in real time, the analysis and then alerting based on it?
The reality is there are very few right now finished quote-unquote products that you can use. The state of the art right now, so if you're not looking at traditional tools that use whatever Gaussian-based parametric techniques, the state of the art right now is there aren't really that many. You have to cobble your own to a certain extent still. I mean, there's a lot of stuff in the open source community, but you have to know R, or Octave or MATLAB and things like that. Python, a lot of stuff is written in Python. Etsy put out last year a tool set in Python. You can find it on GitHub called Kale. So if you Google Etsy Kale, you'll find it. Or go to their blog, Code as Craft. You'll find, but again, they're slowly building on it. They started out with a set of really parametric techniques, but they're starting to add some non-parametric stuff to it. So, but in essence, a lot of stuff is cobbled together right now.
Just one more. Sort of a follow-on from that. I've been doing sort of really basic anomaly detection stuff myself for a couple of years now, but my knowledge of these techniques is very limited. I'm not a data scientist at all. Do you have any recommendations of sort of good places to go where you can find out information if you want to implement some of these things yourself? Without doing a master's or something.
Yeah, my Bible from my grad school days, but it's a textbook, unfortunately, is Duda and Hart. It's a great book. Mark probably knows it, but it's a pretty heavy textbook. Let me think, and maybe I will put together a list. I mean, it's all over the place. There is no one place you can go to. Send me an email, and maybe, I don't know if there's some kind of community group or something where I'll take it upon myself to put together a list of these things. I'm sure there's several out there, but maybe I'll make a list and like disseminate it or publish it. If not, just send me an email and I'll put together a list for sure. It's overdue, and I've been thinking about it for a while, but we should probably put something together as a community for sure. Yeah, but yeah, if you want to buy a textbook, it's Duda and Hart. This is the Bible. This is the best textbook available on these kind of techniques, especially I think second edition or something.
Last question for your time. Great. Well, I will be again.
Thank you very much. Thank you. Thanks.